Everyone, and thanks to my talk. I'm Yuhong from Fudan University. Today I'm going to present our work UIPicker, User Input Privacy Identification in Mobile Applications. This work is done in collaboration with guys in Texas A&M University and Indiana University at Bloomington. Okay, protecting users' privacy in mobile apps has always been at the spotlight of security research. Sensitive data in mobile apps could be either leaked out due to apps' insecure implementation or harvested by intended attackers by leveraging existing vulnerabilities from the mobile system. Lots of program analysis techniques have been proposed to analyze or detect privacy leakage in mobile apps. Existing work like Tandroid monitor user-sensitive data dynamically. Other work like FlowJoid use static analysis to detect and evaluate potential privacy leakage in large scale. Moreover, access control mechanisms like ORSIM protect user-sensitive data through well-defined policies. These techniques are further employed by system vendors or app markets like Google to detect the apps that conduct unauthorized collection of sensitive user data. Critical to those privacy protection mechanisms is the labeling of sensitive user data. However, existing works can only protect sensitive data provided by the system. For example, the GPS locations can only be acquired through system call like getLastKnownLocation, as we call them system-centric privacy data. The more complicated here is the content that user enter to mobile apps through its user interface, which include, but not limited to, users' account credentials and profiles, and location information, which represents one's visited places and delivering address, or financial information like credit card number, security code, and expire date, as we call them user input privacy data in this paper. Unlike system-managed user data, which can be easily identified from a few API functions, the UIP data cannot be found without passing the context and semantics of the user interface. A straightforward approach is to mark all inputs as sensitive, which is clearly an overkill and will cause a large number of false positives. Prior approaches typically rely on users, developers, or app analysts to manually specify the content within apps that need to be protected. This requires intensive human intervention and does not work when it comes to a large-scale analysis of apps' privacy risks. So, to address this issue, we propose UIPicker, a novel framework for automatic large-scale user input privacy identification within Android apps. The identification results can be further used for security analysis or protection of user-sensitive data. Based on UIPicker, we also propose a runtime security enhancement mechanism for UIP data protection, which helps users to prevent their sensitive inputs insecurely leaking out in apps runtime. Our approach leverages the observation that most privacy-related UI elements are annotated by relevant keywords on UI screens or well described in layout resource files. This provides us a potential way to automatically identify UIP data from such textual semantics. This is because text in UI screens usually contains semantic information that describes the sensitive inputs to users. Besides, layout description text in resource files also contain rich semantic information to reveal what the specific element is intended to be in the UI screen by developers. But although UIP data can be easily recognized by a human, it is quite challenging for the machine to automatically identify them. The first problem is how to get privacy-related text. One can easily come up with a few set of keywords about UIP data, like username and password. But due to the highly unstructured character of such semantics, it is very difficult to get a complete dictionary to cover all privacy-related texts. Besides, privacy-related semantics also sparsely distributed in different UIs of the app, which makes it difficult to be efficiently recovered by manual collecting. Second, based on a given set of privacy-related texts, to what extent an element contains privacy-related text can be identified as sensitive. Purely rely on keyword-based search would be some sort of inaccurate in many cases. For example, the term username could always be split into user and name as two separate words, and none of them can represent username. In UIPicker, the UIP data are automatically recovered with novel combination of natural language processing, machine learning, and program analysis techniques. Here is the overview of UIPicker. First, it extracts specific types of layout resources from a given set of applications in pre-processing step. Next, it uses clustering algorithms to efficiently recover a crops of privacy-related text that represent UIP data. Then, UIPicker utilizes such content as features with a subset of UIP data to train a classifier that could identify sensitive user inputs from an app's layout resources. At the last step, it also performs a static analysis on the app's code to locate the element that indeed accept user inputs, thus filter out those elements only associated with certain sensitive keywords, while not actually contain private user inputs. In pre-processing step, UIPicker extracts the selected layout resource text and reorganize them through natural language processing. For each app, we extract UI text and layout descriptions from the decompiled layout files. Then, we use word splitting to separate those delimiter-separated or letter-separated words and remove redundant content such as non-English strings and stop words. We also use Zhemin to reduce the number of texts. For example, we change the word like secured, security into the uniformed format as secure. The pre-processing step can greatly reduce the format variations caused by developers' different coding practice. Since the privacy-related words prefer to be correlated in specific UI such as login, registration, or settings page of the app, if some words appear together in this UI, they are likely to have semantic relevance to user-sensitive information. So, in the second step, UIPicker first automatically labels a subset of layouts, which could contain UIP data with a few privacy-related seeds by heuristic rules. Then, it clusters privacy-related text by comparing each word's appear frequency between those privacy-related layouts and other normal layouts. We use a standard statistical test method named chi-square to extract those texts which can mostly describe sensitive inputs. As a result, these inferred texts can be used as features for the machine learning approach to identify UIP data in the next step. Next, UIPicker uses the support vector machine to train a classifier for UIP data identification from their textual semantics. A single word alone usually does not provide enough information to decide whether a given element is privacy-related. However, all such features in combination can be quite suitable for this task. Since we observed that many elements can also be described by text in its symbol, which is another layout element near it rather than itself. For example, the password field could be described as the short phrase, "Please input your password," just on the top of it. So we also take the symbol elements into consideration as feature well. The training data is generated from a subset of element samples with privacy-related features. Part of them are from elements with explicit sensitive input type labels, like text password. And part of them are manually labeled for the financial inputs. In the last step, we use static analysis to match UIP data behaviors reflected in application's program code. On one side, this step helps us filter out many static labels which only contain privacy-related keywords, while without any user inputs. For example, a dialog box explaining the privacy policies of the app. On the other side, this step also helps us to recover input fields other than the standard type of input field named edit text, which Android provides, like a drop-down list for time selection or customized input field with an arbitrary user-defined name. Here, we show an example of how the behavior-based result filtering is conducted. For each UIP candidate identified from the SVM classifier, we first locate the corresponding element and the layout it belongs to in decompiled application code. Then, we try to find whether the content in this element is acquired by program under specific user-triggered event, which means the data is indeed provided by the user and accepted under her consent. Here, the input field IB is defined in activity add credit card. When the user clicks the add your card button, the onClick function in class add card listener will be triggered by pre-registered system callback set onClick listener. Then it gets the user's card number by invoking getText function, and finally send this piece of data to somewhere else. With the help of UIPicker differentiating UIP data from other normal inputs, we modified Tandroid and use tent tracking-based technique to trace user-sensitive inputs in runtime. If the data is transmitted with plain text or under insecure SSL implementation, we inform users to let them decide whether to proceed or not. The plain text transmission can be easily identified by checking if the tented sink is HTTP connection in runtime. For the insecure SSL implementation, we integrate additional static analysis with previous work Mallojoid to find the broken SSL usage offline for each app. As we show here, a popular Chinese app is intended to collect users' credit card information insecurely during the payment process. This is reported to user with a pop-up window. Thus, the user can decide whether to proceed or use an alternative payment method to avoid the security risk. Now, let's come to the evaluation. The dataset is generated as follows. Excepting some connection errors occurred in the crawling process, totally, we collected over 17,000 apps from Google Play Store, based on its pre-classified 35 categories in October 2014. For each category, we download the top 500 apps. Here, we show the UIP data distribution in our dataset. Overall, more than 35% apps contain UIP data, and they exist in more than half of applications in 9 out of 35 categories, which show that further protection of these UIP data are in urgent need. For example, We observed that categories such as business, finance, shopping, communication, and social are more likely to request account credentials and user profile information, which showed that these apps are closely related to users' personal activities. The shopping category contains many location-related elements because the delivery address are always generated from user inputs. It is also reasonable that both finance and shopping apps require many financial-related sensitive inputs. As previously mentioned, part of sensitive resources, such as phone number, account, and location, can be regulated by fixed system APIs. So we compare the amount of UIPicker identification results with these system-defined APIs, which can help us to know to what extent such APIs are insufficient to cover users' privacy. The results showed there's also a large part of sensitive data exists other than system-centric privacy, while UIPicker successfully identify them. Most of such sensitive data cannot be analyzed or protected by existing works due to the lack of efficient labeling approach. Note, there exists some overlap between these two types of data. However, in most cases, the overlapped data in the same privacy category may come from different sources without overlapping in the code path. For example, the invocation of getLocation API is only used for real-time geographic locating, while some location inputs could be a shopping address for delivering goods. As previously mentioned, in the identification model of UIPicker, we use elements containing sensitive attributes as part of our training data. However, they can only cover a subset of UIP data because they are not intended for this purpose. Overall, UIPicker identifies nearly twice more UIP data than simply identify them by sensitive attributes like text password. Especially for the location category, UIPicker identifies over 50 times more UIP data than those elements with attribute text postal address. We also list identification results of UIP data elements other than the standard type named edit text, which Android provides. In general, UIPicker finds over 25% of elements other than edit text to accept user-sensitive inputs, which cannot be found without the behavior-based result filtering process. It is interesting to note that UIPicker also finds a large number of text view as UIP data elements. We find such UIP data are mostly generated by users from other layouts first, and then dynamically be filled in these text view elements later. For example, the data could be generated from a registration form filled in previous step, or the data is fetched from the server after users log in. As a best effort solution, in the manual validation for evaluating the precision of UIPicker, we randomly select 200 apps from top 10 categories ordered by the amount of apps which UIP data appear most in our dataset. Then we evaluate its false positive and false negatives. Overall, the results show that UIPicker precisely identified most of UIP data with over 93% precision and 90% recall. So in this paper, we propose UIPicker identify UIP data based on novel combination of natural language processing, machine learning, and static analysis techniques. Although the prototype of UIPicker is implemented for Android, the idea can be applied to other platforms as well. We also propose a runtime security enhancement based on UIPicker to protect users' sensitive data insecurely leaking out. Since UIPicker enables to provide additional sources compared to the system-centric privacy data, it can be easily deployed for other existing mechanisms for performing better privacy analysis or protection in mobile apps. So thank you, and please feel free to ask any questions.
So again, we have lots of time. I think it's 25 minutes until the end of the session. So.
Again, this is Haibo from Shanghai Jiao University. I think it's also a very nice talk. Could you talk a little bit about the machine learning part? So you mentioned that you have a set of training to training the super support vector machine.
Yes.
And do you need develop to manually doing some labeling or using?
Yes. We manually labeling the financial category about UIP data because there's no explicit sensitive attribute to label this type of privacy.
Okay, so what's the size of the training set?
The training size is about over 6,000 elements.
6,000 elements?
Yes,
okay.
Yes.
I see, cool. Thank you.
Can you talk a bit about the false positives and false negatives? So what are the hard cases for the system?
Okay. The false positive are mainly come from the symbol elements. That is the UIP data identified as false positive is actually the actual UIP data just on top of it or under it. It could be identified as false positives. But we consider once such false positive happens, it does not affect the further analysis or protection because once the false positive happens, the actual UIP data is indeed to be identified as well. Both of these similar these symbol data share the same transmission or storage channel. Yes, and for the false negative, it mainly comes from the static analysis part for the behavior-based result filtering. Since we implement the static analysis based on suit and FlowJoid, the call trace about some UI element may be broken. That makes the false negatives. Yes.
And how about layouts that are generated during runtime? So can you handle those?
Actually, we also cannot take the dynamic generated layouts into consideration currently. Yes.
That's Yamori, Waseda University. Is your method applicable to other languages?
Excuse me.
Okay, can you apply your method to other languages like Chinese or Japanese or something?
Oh yes, that's a very good question. What we utilized is the layout resources, which is not just the UI text on the screens. It also contains, we also take the text in the XML files into consideration as well. So if the developers write sensitive UIP elements, it must contain the English text in its files, so we can identify them. Yes, thank you.
And then I have one last question. So you had about 35% of the text or of the input fields are somehow sensitive. In the super talk, we heard about 30% of the input fields that they identified as being sensitive.
Yes.
So is there some kind of, or can you comment on that? So what's your intuition? Why did you identify more? Or is there a bias on the sample set?
This is mainly because we take the location category into consideration. Many of them are, and the super does not include it, as I remember. And yes, what we missed compare with super is the health data. And why we identify more data than super is part of them are because we identified customized widget elements, and text views, which Super did not consider. Yes.
Okay, thanks a lot. And if there are no more questions, I would like to close the session. Thank you all for attending, and then see you next year at USENIX 2016. Thank you.